In this video, we're looking at the motion of a 5 kilogram block that has a 10 kilogram slab stacked on top, and that slab is held in place with a horizontal string. An external force acts to the left on the 5 kilogram block, pulling it to the left with a constant velocity. We're told there is kinetic friction at the lower and upper surfaces for the 5 kilogram block, and the coefficient of kinetic friction at both of those contacts is 0.2. Now our main goals in this problem are to find the magnitude of the force F and the magnitude of the tension in the string T. So the problem is broken into 3 parts. First, we want force diagrams on these blocks showing all weight vectors, normal forces, and friction forces. So we can pop the weight vectors into the diagram. And here I'm using a subscript of B for the bottom mass, that's the 5 kilogram mass. So when we look at that weight vector, it has a magnitude of mb times g, that's 5 kilograms times 9.8 meters per second squared, and we get 49 newtons. The slab on top, that's mt, and 10 kilograms times 9.8 meters per second squared, that's 98 newtons. Now it's very simple to figure out what the normal force is on the 10 kilogram slab at the top. If gravity is pulling down with 98 newtons, then there must be a normal force exerted by the 5 kilogram mass pushing up on the 10 kilogram slab equal to 98 newtons. That normal force of the 5 kilogram block pushing up on the 10 kilogram block, that has a reaction force of the 10 kilogram block pushing down on the 5 kilogram block with exactly the same magnitude. That's Newton's third law. And in the diagram, I called that F5/10. That's the force on the 5 kilogram block due to the 10 kilogram block pushing down on it. And now that we've got both downward forces on the 5 kilogram block, it's simple to find the normal force on the 5 kilogram block. That's the force from the floor pushing up on the 5 kilogram block to balance both of those downward forces. Now I went ahead and computed that normal force already. It's just the sum of those two downward forces. There's 49 newtons and 98 newtons pointing down. The sum of those is 147, so the normal force pointing up better be 147 to balance those. Now we can get into our friction forces. So as we saw in the animation, as this 5 kilogram block was being dragged to the left under this 10 kilogram slab, it was slipping to the left over the bottom surface and slipping to the left under the top surface. Those both produce friction forces pointing to the right on the 5 kilogram block. And I'll just go ahead and leave those symbolic for the moment. One of them is Ft, the friction force exerted at the top surface of the 5 kilogram block. And that's given by our kinetic friction coefficient multiplied by the normal force at that contact surface, which is Nt, or 98 newtons. The friction force exerted at the bottom surface, that's mediated by a larger normal force of 147 newtons, or Nb. And we'll go ahead and calculate the numbers on these later. Now there's a couple things left to do for the slab that's on top of this 5 kilogram block. First, if there's a friction force exerted to the right on the 5 kilogram block due to the 10 kilogram block, then Newton's third law guarantees that the friction force exerted on the 10 kilogram block from the 5 kilogram block is opposite in direction but equal in magnitude. So that's another action-reaction pair in this problem. And hopefully this makes sense intuitively as we're dragging this 5 kilogram block under the 10 kilogram block. It's trying to drag that 10 kilogram block to the left. The final force that we need to get into the diagram is the tension pulling in that string. And that tension, of course, is one of the unknowns that we're trying to solve for. Now, I want to point out before we move on that it's practical to solve this problem without ever showing the weight vectors. You can figure out the normal force on the 10 kilogram mass has to be 98 newtons in order to hold it up against gravity. You can figure out the normal force on the bottom surface by just saying the normal force has to support 15 kilograms. And if you take 15 kilograms times 9.8 meters per second squared, you get the same 147 newtons that we got. But I wanted to take the time to have a 100% complete force diagram for this problem. So this is it. Now in part B, we're trying to get the magnitude of the force F. And the critical concept here is that this 5 kilogram block is in equilibrium. It's moving, but it's moving with constant velocity. That means the net force on it is 0 and all the forces left and right are balanced. So I'm going to start by actually getting numbers on those rightward pointing friction forces, and then we'll go ahead and find big F. So the friction force at the top surface is mu k times the normal force exerted at the top surface. That's 0.2 times 98 newtons. And when I run the numbers on this, I get 19.6 newtons for that friction force. The friction force exerted at the bottom surface is mu k times the normal force there, 0.2 times 147 newtons. And this gives me 29.4. newtons. And we know this block is in equilibrium, so all the forces are balanced. Big F is our force to the left, and that's got to be equal to all those forces pointing to the right, 19.6 plus 29.4. And we get a total of 49 newtons. Finally, we want to find that unknown tension in the string. So now we're analyzing forces on the 10 kilogram block. And there's not much going on to the left and right. I see a friction force pointing to the left. That's the friction force at the contact between the two blocks. We already computed that as 19.6 newtons. And the only force pointing to the right is the tension itself. Since that block is completely stationary, that's in equilibrium as well. These forces are balanced. My tension is going to be equal to that leftward pointing friction force in magnitude, and that gives me 19.6 newtons. And we're done. If you enjoyed this video, or at least found it useful, check out another one by clicking one of the links on the left, or click the Zach's Lab logo on the right to explore dozens of physics and math playlists. As always, you can leave your questions, comments, and requests in the comments section below, and I'll get back to you within 24 hours. Thanks for watching Zach's Lab, and best of luck on your math and physics journey.